In our first video, we looked at the two-way analysis of variance in terms of its logic. We saw that it was a two-stage process, the first stage being just like our one-way ANOVA that breaks down all of the variability in an experiment into two components, a systematic component of variability between groups and a random component of variability within groups that we call also an error component. Although it does not mean something was done wrong, it just means the variability around the group mean that is not due to the systematic treatment. In the second stage, we took the systematic component, the part that defined the various groups and the differences among them, and analyzed that into the part that was attributable to two different factors and the possibility of an interaction between the factors. We saw how the sums of squares would be divided by their own degrees of freedom to create a mean square, one for each of the factors or main effects and one for the interaction, so that we could carry out 3 f-tests. In this video, we're going to do all of those procedures using Excel to carry out the computations on a real data set. At the very end of our last video, we looked at some data from the Texaco company that was in the process of putting out a new type of filter called Octel and wanted to compare it with the standard filter on 3 kinds of cars: small, mid-size, and large, and the dependent variable was noise. There had been complaints that this pollution-reducing filter might in fact make cars noisier, and so they carried out a test to find out if it were true, looking for the main effect of car size on noise, the main effect on filter type on noise, and the possibility of an interaction. And by using a two-way ANOVA, they could look at car size controlling for the filter type, and look at filter type controlling for the car size, and then look for any possible interactions. In this video, we will let Excel carry out the computations. If you are a Mac user, that XLMiner Analysis Toolpak will work in almost an identical way on your Macintosh computer. This shows you the results that we will have at the end of the analysis. You can see that our data are already here over in the upper left-hand corner. The output that I will get from the Toolpak is everything that's on the right-hand side of this screen. So all of this came out at one fell swoop from one set of commands in the Toolpak. I used that data to put together a little table of means, and then from that table of means was able to generate a graph that will be useful in my write-up. And we'll see how all of these steps are carried out. You will see that I've got a lot of color in this particular image. I like to use color in part for your sake to make the components easier to see, and in part for my own sake for the same reason, that it helps me see exactly where the various elements are. The output that I get from the Data Analysis Toolpak does not have the color in it, so don't be surprised when you run your analysis and find that no color shows up in the results. You may find that it's worth the time to color in the various components so that you too can have the assistance of seeing how the different components work together. The first step is actually carrying out the analysis using the Toolpak. In Excel, I click the Data tab and go over to the far right and choose the Analysis Toolpak. If I'm working in Google Sheets, I will go to the add-ons and run that XLMiner Analysis Toolpak, and over on the right-hand side of the Google Sheet, I will see a menu of possible analyses. Either way, I'm having a menu that looks pretty similar in terms of the items listed to the one that's on the screen here, and the thing that I'm looking for is two-factor with replication. That with replication means that each unit sampled is chosen independently from the entire population. So it's a statistical term that goes back to our probability. When we do look at a repeated measures ANOVA, we'll find that it's the second element here, the one that says without replication. That would be the situation where if I measured somebody before they entered treatment, 1 week after the treatment and 6 months after the treatment, a repeated measure, all on the same people, they are not they aren't with replication because I've in fact used the same person over and over again in the study. So for this one, we're looking at two-factor with replication. Once I choose that, a menu will pop up in which I give the actual commands. Once I chose two-factor with replication, I get that dialog box, and the first thing I have to do is put in the range in which my data are found, and you'll notice that this includes not just the numbers, but I selected the entire data area, including the labels. Those labels will show up in the output, and it makes it much easier to understand. ANOVA will go about doing this with just the numbers, but the results are much more difficult to understand. It asks me how many rows there are per sample, which lets us know that this particular type of two-factor ANOVA requires that I have groups of the same size. And then it lets me put in the particular alpha level that I'm comparing against. And then finally, I have to select where I want the output to go. It's going to be rows and rows and columns of output, but I only need to designate the upper left cell. So here I've selected G2, and that's the number that when I selected it showed up in the box down below. As soon as I hit OK, we'll get the results that show up on the next slide. As soon as I click on the OK button, I get quite a bit of output, and at first it might seem kind of daunting. The thing to recognize is that it really breaks down into two components. The part at the top that says Summary is really a set of descriptive statistics about my data set, and then the part at the bottom that's labeled ANOVA is my actual analysis of variance table. And we'll look at each of these components separately in some of the upcoming slides. First, let's look at the descriptive statistics. And in this little image over on the right, I've showed you where I pulled this out from the original data set, and I've colored in the cells so that I could see the impact of the three different sizes of cars, and then I've looked at my two types of filters in green and blue. So within the 6 cells in the middle, for each of the groups, I can see the mean and the variance, which would also let me compute the standard deviation inside each of the 6 groups. Over on the right, I have an additional column labeled total, and in that total column, I would be able to compare the mean for the standard filter to the mean for the octal filter across all 18 cars that had each type of filter. So this lets me compare the filter types without regard to the size of the car. I've controlled it by looking at just the filter type. Down below, I'm able to look at another total column, and this would let me compare the mean for small cars with the mean for medium cars and the mean for large cars. And if you remember, this variable is noise level, so we're seeing that the small cars have somewhat quite a bit of noise. The mid-size cars actually have more noise, and the large cars are quietest of all, and this is without regard to filter type. So these totals along the edge are letting me look at the impact of one factor controlling for the other, and then we'll be able to look for the interactions that might occur in some of those middle cells. While I'm looking at the descriptive statistics, one of the things that's a good thing to do is to create a small table. You can see I've got it started over on the left-hand side that has the means, and I could put in the standard deviations as well, but I chose to only copy the means. So I'm going to get the means just of the standard group and put them in the top row. I'd copied the labels as well. And then I'm in the process of grabbing the means from the octal group and moving them into the second row of my table. This will be useful in my write-up, and it will also make it easy for me to create the graph that you saw earlier in this video. Once I've captured those means and created my table, I'm ready to go on and look at the second part of the output, where the actual analysis of variance table is found. This two-way analysis of variance is going to produce 3 different F-tests. One will be for what the Excel Data Analysis Toolpak calls the sample. That in this situation is the filter type. The other is the columns. In this case, it's the car size, and then one for the interaction. And for each, we see a sum of squares. We see the degrees of freedom computed. Going across, the sum of squares divided by the mean square, by the degrees of freedom, produces the mean square. When we do that computation for our error term, we get the denominator that is used in all 3 of the F statistics. So our filter type analysis of variance takes the mean square that we have for the filter type and divides by the within sum of squares to compute the first F statistic. The second one looks at car size, divides it by the same within squares mean square to get the second F statistic. And then my interaction takes the mean square for the interaction term and divides it yet again by the same denominator, the within sums of squares divided by its degrees of freedom, to produce its mean square. For each of these F statistics, Excel, or if you're working with Google Sheets, the Google Sheets produce the p-value, and the p-value is the way I decide whether something is significant. I was planning to use an alpha of 0.05, but because I have the actual p-value, I have the possibility of also comparing to 0.01 or even 0.001. So when I look at the main effect of filter type, I have a p-value of 0.0003. That number is less than 0.05, which means that my result is significant. My 0.05 level meant I would have 5 chances in 100 of making a type 1 error, and I wanted to say something was significant if I had that risk, 0.05, of a type 1 error or less. And I have a risk that's quite a bit less. It's not only less than 0.05, it's less than 0.01, and it's even less than 0.001. So the main effect of filter type is very significant. I look at, in the second situation, I look at the main effect of car size, and here you see an interesting situation. Nothing shows up but zeros. And in fact, when this first showed up on the screen, I was seeing scientific notation. It had the letter E in the middle of it, and I had to convert it to even see these decimal places. It does not mean that the probability of getting this result is 0. It means that there are some digits out to the right, but I might have to be able to show 10, 12, 15, 20 digits before I would be able to see them. It means that my p-value is less than 0.05, it's less than 0.01, and it's less than 0.001. I could report that it's less than 6 zeros and a 1, but I'm unlikely to go that far in a write-up. I would probably just report that it was less than 0.0001. And finally, if I look at the third result, the interaction term, my p-value is less than 0.05, and it's less than 0.01, but unlike the others, it is not less than 0.001 because the p-value here is actually 0.005, and that's greater than 0.001. But I am going to call all of these a significant result. In the Excel Data Analysis Toolpak, the Toolpak goes one step further, and it does show me the critical value. This is the value that I would find if I looked in an appendix like the one in the back of our textbook, and it lets me see the same result if I compare my calculated F, the one that was actually computed for the data, with the critical value. You'll see that my computed F is larger than the critical value in all three cases, and you can see why that middle car size variable has such a teensy p-value. My actual F statistic is 199, and I only needed an F of 3.13. 3.31 in order to reject the null hypothesis. So this 199 is much larger than the 3.31 that I needed in order to make the rejection. So now that we've walked through an actual analysis of variance table for a two-way ANOVA, you should be ready to use the ANOVA table quizzer to practice understanding these relationships on your own. And I do recommend very strongly that you use that ANOVA table quizzer to practice so that you'll be ready for a question like this when they show up on the exams. We do need to be able to say something about effect size. We know that we have results that have a low probability of being due to random chance, but we don't know how big the effect is. In our textbook area on effect size, it shows us how to compute eta, which is another Greek letter. It's actually kind of like the Greek letter H, but it's become pronounced more like a vowel, eta. But in fact, eta squared is a more useful statistic, and you'll find that in the equation in the textbook, it's showing you a square root of something, and the something is eta squared. In this situation, I'm going to show you how to compute eta squared. If we put a square root around it, we'd be computing eta just like the textbook. Eta squared is a fraction, and it has the sum of squares for the particular effect, or we could say for the particular factor in the numerator of the fraction, and the sum of squares total on the bottom. And so it's actually answering a question that makes good sense when we ask it. The sum of squares total represents all of the variability that there is in the data. So this fraction says, out of all the variability that exists in the data, what proportion is related to factor A, the car size, or factor B, the filter type, or the interaction? And if we take this fraction and multiply it by 100, we can report it as a percentage. And that's very useful, as you'll see in the third video when we actually report these results. Because the sums of squares are available in that ANOVA table, it's possible to create a column of eta squared. I added it over to the right by just carrying out the division. I've already computed the first one, and I'm showing you how I'm doing the computation here so that you would be able to do it on your own when you're doing the Excel homework. So you can see that I've put in an equal sign to start the equation, and I've clicked on the sum of squares for a column variable. In the situation we have, that it's the size of car, and then I used a slash for division and clicked on the total sums of squares that's down below, and when I hit enter I'm going to get a fraction, a proportion, because the sum of squares for the columns will always be less than the total. So when I hit enter I will get another proportion, and then I would go on to do the same thing for the interaction sum of squares. Here we see what the results are when I've completed all of the computations and colored in the column as gray. So we can see that out of all the variability in car noise level, 3.54%, that's this proportion just multiplied by 100, is related to the type of filter. So remember, I knew that there was a significant result. This is letting me say that I would not get the results I did by random chance, but this filter is really only explaining less than 4% of the noise variable information. In contrast, out of all the variability in car noise level, 87% of it is related to the size of the car, controlling for the filter type, and that's obviously the vast majority of the variability in noise level. And then if you remember, I did have a significant interaction effect, and that interaction effect that I don't yet fully understand, I haven't seen it, accounts for about 2.69% of the variability in noise level. And then the remaining variability is related to all the other random factors, different makes of cars, different particular cars, etc. These particular eta squareds are a little bit unusual. You hardly ever see in social science or medical data anything that explains 80% of the variability. There's usually so much more randomness going on because human beings are nowhere near as similar to each other as cars are. So this 87% is quite an unusual number. Usually we would see that the random component is much larger. So if you remember, our effect size says how much impact did I get from an effect. I only compute effect size if I had a significant f-test. In this situation, all three of my tests showed significant results, and so I computed all three eta squareds. The last thing that I want to look at is a graph, because the graph helps me understand the interaction effect. And what I'm graphing are the means in each of the 6 cells. So I've arranged the means for small, medium, and large cars with the standard and with the octal filter. And when I select this entire part of the data, including the labels, and use the Insert tab and choose a line graph, I get a result that looks like the one below. And this lets me see that for small cars, the octal filter was slightly quieter, but not by very much. And for large cars, the octal filter was slightly quieter, but not by very much. The interaction is showing up in the mid-size cars. In this group, the octal filter was quite a bit quieter than the standard filter was. So I can see that I have the impact of filter. It's always quieter to have an octal filter. And I can also see the impact of car size. Both the small and the mid-size cars are noisier than the large cars, but my interaction effect is shown whenever my lines diverge or the other thing that sometimes happens is that lines could actually cross. Whenever I get a line graph where the lines diverge and make a trumpet kind of shape, where when they cross, it lets me know that I probably have an interaction effect going on. So I've now seen all the aspects of my analysis. I am ready to do the write-up, and that's what we do in the third video. When we look at the write-up, we'll use the same sandwich method that we have in our previous hypothesis tests, but as you can imagine, it has quite a few more components because of the 3 f-tests and the various elements that we ran for effect size. So in the next video, you'll have a chance to see how all of those components go into the write-up. Let's dig in.